There we go. So, hi everybody. We are beginning chapter 3 today. I just got caught up on grading and everything is in place. So that's really positive. And we're going to begin chapter 3. And as you can see, there's quite a bit of material to cover in chapter 3 as far as the textbook goes. And what we're talking about here is a direct continuation of our work in chapter 2. And basically, what we do in chapter 3 shows us how to apply the ideas that we learned in chapter 2 and why we are interested in applying that. So, hang on a second. I want to make sure I've got the right screen up. Sometimes it does not record the way I want it to. All right, there we go. So when we talk about the ideas of chapter 3 talks about two different concepts. We've already talked a lot about forces. And the next thing that we're going to talk about is moments. Okay, so basically, the way that I always think about this is that a force, if it is not opposed, produces or tends to produce a linear motion in the direction of the force. And specifically, the motion is an acceleration. A moment, on the other hand, if it is unopposed, produces a rotation. Right? So mathematically, what we can say, in order for equilibrium to occur, which means no acceleration, we can say that the summation of forces in all vector directions has to equal 0. And for no rotation to occur, the summation of moments about any given point also have to equal 0. So this brings up an interesting idea. A moment is a force acting through a distance. So some examples of this would be if, for example, you have a nail that is firmly embedded in the ground. And if you just took your little fingers and tried to pull that nail up, that would be very difficult because of many, many things. But let's just talk about the force. If, on the other hand, you used a crowbar or a pry bar and you pulled down on it, if you pulled on it from here, it would be somewhat easier than pulling up. And if you pulled on here, it would be even easier. And the reason is that you can transmit a force through a distance and it will be more powerful than it is just a force alone. Or if you ever see, if you have like a really hard nut to break loose and you have a wrench, you can put a cheater bar on it to give yourself some more length. So all of those things have to do with moments. Another example is if you think about, I don't know if you guys have ever been on a teeter-totter. It might be a thing of the past. But a teeter-totter basically has a pivot point. And if you put a child here and a similarly weighted child here, you're really not going to go anywhere. Everything's just going to be balanced. But if you put, if you move that pivot point, say to here, then this child, even though he or she weighs the same as this child, is going to pull that teeter-totter down. And that's kind of used to be a famous trick of older brothers and sisters to keep their younger brothers and sisters suspended in midair for long periods of time. So the kid had to jump off eventually. But anyway, those are just some examples of moments. Now, moments become very, very important because for us and our work here in statics, right now we know that the summation of forces in vector directions have to equal 0 in order for things to stay still. But it turns out that the moments have to equal 0 as well. So mathematically, we'll deal with that in chapter 3. Or we'll begin to deal with this in chapter 3. Now, there are some ideas about forces that they talk about here that are sort of important, but the first is the difference between an external force and an internal force. An external force is just something that you apply to a force or to an object, and an internal force is something that comes about because of the body itself. For example, weight. Weight is a force, but it's not external to the object. Pulling on an object with a rope would be an external force. There's also within external forces, they don't talk about it too much here, but there are, we'll go ahead and talk about this so we have the verbiage. External forces can be either applied forces, like the guys pulling on a rope on the front of that truck, or they can be reactive forces. So in other words, some forces are not applied, but they are just reactions due to the nature of the object. So for example, if you look at the truck, the guys pulling on the truck is an external force, and it's also an applied force. However, in order for the truck to sit on the roadbed, the roadbed has to push back up on the truck. And although that is an external force, it's also an applied force. And it's sort of like if you have an object like this table and you push down on it a little bit or you roll it a little bit, the floor will push back some, but it won't push back a lot. If you weight this table heavily or you push on it very heavily, the floor will push back with the same reactive force. So it can change based on how you configure things. And the only time that stops is when you break the floor or you damage the table because the force is too heavy to bear. And we don't talk about that in statics. We just pretend like everything is strong enough to bear every force that an object is subjected to. And we'll talk about things breaking in mechanics and materials. So that will be fun as well. But not today, so you don't have to worry about it today. The principle of transmissibility basically says that a force acting on an object has what is called a line of action. And the line of action is just directed along the force. And if you pull on it anywhere, if you move that force anywhere along the line of action, it's going to be an equivalent force system. It can change some of the rotational properties of the object, but as far as the force itself, you can think about it being applied anywhere along the line of action, which is just a line through the tip and the tail of the force as you draw it. Okay. So here, for example, when we get back to the truck, what they're saying is it's exactly the same to pull on the truck with a force F as it is to push on the truck with a force F. So that's, and actually the principle of transmissibility is really built into the idea of adding and subtracting forces or vectors in general, but we won't get into that. Okay. The next thing we talk about, and I believe this is going to be the last thing we talk about today because it's kind of new. We might go into we'll go into 3.1D. I just want to look ahead here and make sure I'm not going too far. And we'll go all the way up through 3.1e. Is there a 3.1f, or do we get to 3.2? We'll probably stop there. Okay, so when we start talking about this next part, we start talking about products of vectors. All right, and the reason that we talk about products of vectors, there's a mathematical reason and a practical reason, which is also part of the mathematical reason. But there are two types of vector multiplication. There are what are called dot products. And a dot product is also more correctly called a scalar product. And then there is a cross product, which is more accurately called a vector product. Well, what that means for us is that a dot product is two vectors. It's the projection of one vector onto the other, mathematically. And unknowingly, we were kind of doing that when we were taking components. So like if you have a vector that looks like this, V, and we have an angle theta that it makes with the horizontal or x-axis, we can say that the component of V in the x direction is equal to the magnitude of V times the cosine of theta. And geometrically or trigonometrically, it looks like this, right? And that is actually a scalar. Now, this always irritated me when I was a student because the simple definition of a vector is that a vector has a magnitude and a direction. And the component of x, of V in the x direction, has a direction. The direction is x. And that always bothered me. However, I have come to understand that the real meaning of vector is more complicated than that. What basically happens is a component is a projection and it doesn't have enough directional properties to be a true vector. So the way that we make it a vector, and this is the part you've already done, is to dot it with a vector I, or to take it in the I direction. So you take a component and you place it along an axis. So you take a scalar and multiply it by a vector I, which has a unit of 1 or a length of 1, and then this is a vector component. So this is not enough directional to call a vector, so it's scalar. And this has enough directional component to call it a vector. Kind of a fine line, but everything works. This is a magnitude. This is a magnitude times a direction. All right, now what about a cross product? A cross product is mathematically what we need to do to find a moment. And it is clearly, unabashedly a vector. Okay, so what that means is, let's take, let me do something relatively simple. We have a boom anchored at the wall, and we have a sign hanging down from that, from this boom or beam or support. And so if we were to take this support, we recognize that weight of the sign always acts downward, that this weight of the sign is going to create a moment about this point. In other words, if the wall does not hold the beam in, this is going to start to rotate in this direction. So first of all, there's some things that we need to think about. One is, as this gets longer, that moment gets bigger and bigger, doesn't it? So in other words, if you hang the sign very close to the wall, you're going to have a smaller moment than if you have it hanging out further. So here's another interesting property of vectors, and I'll try to do this with right-hand rule. But basically, if you think about this length, this boom as being a vector that goes from the wall, which would be, we're going to call that point O to start using the proper nomenclature here. And it goes to some point here, which we'll just call L. This is going to be a purely x directional boom. W hangs straight down, so it's going to be purely y directional. Well, if you think about it, that's going to rotate in a particular direction. So if you think about the right-hand rule, if you have this in physics, where you take the vector O, which goes from point O, excuse me, the vector L, the boom, from O to L, and you fold it into the force, which goes down, you look at the direction of your thumb is pointing out of the page or out of the plane of that action. So there's a few things that we learn about this. First of all, this is the cross product. That's what the right-hand rule is all about, is determining cross products. The cross product is always perpendicular to the plane that the two vectors act in, no matter what. If my sign was like this and my boom was like this, my rotation would be along this axis. So what does it mean to have a rotation that's pointing out of this plane? Well, it means that the axis is spinning around, or it would tend to spin around. So it's not a direction movement, nothing's moving in the z direction. What it's saying is, if you look at the spin, and you think about it spinning about an axle or an axis, that spin would be in the z direction. But the spin will always be perpendicular to the plane that the two vectors exist in. Or in a more general sense, a moment will always be perpendicular to the plane of the two vectors that form its cross product. They comprise its cross product, right? So, vector math does something kind of, well, it's pretty, let's take a look at two different things. So we can do two things with a cross product, which I'm just going to show you the one briefly because it's not all that interesting to me. But the vector that is the axis of rotation, here we have two vectors that are on this plane, and if we cross P with Q, we can use the principle of transmissibility, and we can see we would have P like this and Q like that, P like this. We'd have to use the principle of transmissibility. Let me draw this out a little bit better. Okay, so if Q and P are in the plane of the paper, and we're going to fold, the way we have it, we're having P times Q, so we're going to fold P into Q through that angle theta, and our vector goes straight up. So that means that the rotational axis of those two vectors, or the moment of those two vectors, is going to be straight up in the direction of V. It still follows the right-hand rule. Okay. The magnitude of that vector is and this is some more stuff that I want to show you. You'll notice that these are not bold, right? So this means not vector P or vector Q specifically, but it means the magnitude of P times the magnitude of Q times the sine of the angle between them when you put their tails together is equal to the magnitude of V. Here it's written in vector form. The vector V is equal to the vector P crossed with the vector Q. Now, another thing I want to point out here is vector multiplication is not associative or commutative. It's not associated with commutative here. So in other words, P crossed with Q looks like this. Q crossed with P looks like this. So what that tells us is that P cross Q is equal to negative Q cross P. Okay, so we know with regular, just scalar numbers, 3 times 2 equals 2 times 3. Vectors, not so much. So the magnitude will be the same, but the direction will be 180 degrees opposite. They're both still perpendicular to that plane, but one of them is going to be this way and one of them is going to be this way. Okay. So this is just a little bit of vector math. Talks about that Q cross P is equal to negative P cross Q. And this is the distributive property. Turns out, even though vectors are not commutative, vector multiplication is not commutative, it is distributive. So if you have P crossed with 2 vectors added together, you can distribute the P through the parentheses, and it's P cross Q1 plus P cross Q2. And it does hold. All right, so the reason I bring this up, the last property that we always talk about with multiplication would be the associative property. So if you cross P with Q and then cross that product with S, it's not going to be equal to P crossed with Q crossed with S. So in other words, the order matters, the one that you do first matters, but the distributive property holds. So associative, no; commutative, no; distributive, yes. Okay. So the other thing I'm doing this to show you is this little equation is of limited usability. When we talk about the magnitude of vectors, sometimes we have to, but it's if you have enough information to execute vector math and to do a cross product, you're just better off every single time. And once again, just like when we were talking about in chapter 2, I don't like to use the triangle rule or the parallelogram rule because there's no applicability into the third dimension. It's exactly the same here. If you have an X and a Y vector and you want to find a Z cross product, that little rule for magnitude will be great. Then all I have to do is decide if it's positive or negative in the Z direction. However, if you're operating in 3-dimensional space, it won't help you. So you need to just cut to the chase and use the vector map. At which point you probably say, what does the vector map look like? Well, it turns out that if you're going to do a cross product, to execute a cross product, the first thing you do is to write your vectors in vector notation. And then you don't really have to even keep this in mind, the positive and negative situation. But if you, these pages will show you how to do a cross product. And the easiest way to do it is to use an array. Now, like Oz in our work with MATLAB does this in a second. It's absolutely brilliant. But we can also do it by hand. We're only going to do 3x3 arrays, so it's not that much work. If you do more than 3x3, it gets progressively harder. But basically what this says is if you have 2 vectors, and let me write these out, vector P over here. And I'll also share with you that my physics colleagues always kind of roll their eyes when I do this because this is definitely a cut to the chase math idea. In other words, this is an execution. Why this works is quite complicated and it means a whole lot more than what I'm letting on. But that's math teachers and physics teachers can spend a great deal of time on this. But for us, let's just kind of cut to the chase and learn how to do a vector cross product. So if we have vector P that has the components P sub X in the I direction, P sub Y in the J direction, and P sub Z in the K direction, and we have a vector Q that looks the same as that, and we want to find P crossed with Q. The easiest way to do that is to set up what is called a determinant. And the determinant, if we want to call this equal to V, let's do this in better form. V is equal to P cross Q. We set up a determinant, which is these 3 rows and 3 columns of numbers. And we make the first row goes across I, J, K. The first row is just those unit vectors, I, J, and K. The second are the second row is in order the components of the vector P, and the third row is the components of the vector Q. All right. Now, I'm going to write this off to the side here. Let's see, I should probably stop the share. The reason that we're interested in this specifically is because if we get back to this idea of a boom and a sine, and we want to find the moment in this case is going to be this vector, which is usually called R, just by convention, and this force, which is called F. So everything I do for these general vectors works for creating, for calculating a moment as well. Right. And the other piece is when you have moments, you always have to specify a point that they're taken about. In other words, where that moment arm or where that boom begins and where it begins, and then also where it ends. But O would be the point where it begins. All right. So to find a determinant, they use this little method, which they describe. You duplicate. There's 2. I'll just go through this with you, and then I'll show you how I prefer to do it. But you take so remember, rows go across and then columns go up and down. So you take the first, you write out your determinant, row, 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 and then next to it, you reproduce the first 2 columns, not all 3 columns, but the first 2 columns. So this one begins with I, and this one begins with J. Then you do a diagonal through the first, and everything in the diagonal, there'll always be 3 elements, and you multiply those. Second, multiply those. Third, multiply those. And then you can see you don't have any more rows of 3. So instead of going left to right, you come back over and you go right to left and pick up the 3s, the ones that have 3 in the diagonals. All right, to multiply these and add it to the product of these and add it to the product of these. So every diagonal that starts right to left is positive. Every diagonal that goes left to right is negative. So in other words, you go multiply this, plus this, subtract this, and subtract this. And what you will get, you'll see, because everything will have an I, J, or K in it, you will get I times something, J times something, and K times something. And when you do that, you will have a vector, after you simplify it, that will have I, J, and K components. All right. So at this point, at this strange point, does anyone have any questions? So what I'd like to do next is just show you how this looks, how you multiply 2 vectors together. I'd like to get to where we can just do some math rather than having to, we may not be able to, we may have to incorporate some other stuff. Okay, let's look here at number 316. We have the vectors P and Q are 2 adjacent sides of the parallelogram. Oh, this is what I want to do is I just want to take these 2 vectors P and Q, okay, and I just want to multiply them together. So this is just a math exercise to kind of get us started. So taken from problem 316, I'm going to write out vector P and write out vector Q and then show you how to multiply them together. So P is negative 2I plus 2J minus 6K, and Q is 8I plus 2J plus 4K. And so I just want to know, I'm just going to call it I'm just going to call it R, kind of resultant, is equal to P crossed Q. And how do I do that? All right, well, I set up a determinant. My top row is IJK. My middle row are the components of P, minus 2, positive 2, negative 6. My third row are 8, 2, and 4. All right. Using the method that your authors use, you would reproduce the first two columns. So I would write out here, I, negative 2, 8, J, 2, and 2. Then I would multiply this diagonal, where I have 4 times 2, which is 8 times I, or 8I. Multiply this diagonal. Negative 6 times 8 is negative 48J. And here, negative 2 times K is negative 4K. And each one of those retains its sign. Now I come back up the other way, and I multiply 8 times 2 times K, which is 16K. But this time I have to subtract. Everything that I go from left to right is subtracted. Then I get 2 times negative 6, which is negative 12I. And 4 times negative 2, which is negative 8J. All right, now I have a little simplifying to do. I'm going to break out this negative sign, distribute the negative sign. So I get negative 16K, negative times negative is positive 12I, negative times negative is positive 8J. So now gather up the I's. 8 plus 12 is 20I. J, I have negative 48 plus 8, which is negative 40J. And then negative 4 minus 16K, which is negative 20K. So the vector R, or the cross product of those two, is written like this. If you have, depending on your calculator, you may be able to do this on your calculator. If you do it by hand this way, how easy do you think it is to make an arithmetic mistake? Very easy. So make sure you show me all of your work. If you were to do this and make a tiny arithmetic mistake, you would not lose any credit. Okay, so make sure you show me your work. All right. The other way to do this is, oh, maybe I shouldn't. I'll just describe it. No, I'm not even going to describe it to you today. Let's just stick with this. I'll do the other method next time so that I don't want to overload anything right now. All right. So that's how you multiply vectors. Now let's just do a little proof. We had said that that vectors are not commutative. So what if instead of saying P versus Q, let's say vector S is going to be Q crossed with P. So that means when I set up my determinant, my first row is still going to be IJK, but now my second row is going to be my Q values, which is 8, 2, and 4. My third row will be my P value, which is negative 2, 2, and negative 6. All right. Duplicate those first two columns. Okay. And now I'm going to do this, and I get negative 12I, this, negative 8J, this, 16K. And now when I go the other way, I need to subtract. So I get negative 4K, 8I, negative 48J. Then distribute that negative sign through. Negative times negative is positive. And then gather my i's. I have 12, negative 12 minus 8. So that's negative 20i. Then I have negative 8j and positive 48. So that's plus 48j. And then last but not least, 20k. Okay. And if you see then the relationship between R and S, the magnitude of each component is the same, but each sign is different. So what that means is they're 180 degrees apart. Right. Lots of direction. So do you guys have any questions at this point? All right. Well, I think that's going to get you started. Take a look at the other videos and you can apply these. The first parts of the homework are really in 2 dimensions. So what you basically do, let me draw you a free body diagram here. Just to get started. Let's take a look what the first homework problem is. Okay, the first homework set is 3.1, 3.3, and 3.22. So I already kind of talked about a lever. Let's look at 3.1. This is a foot valve. This is sort of like, even though it looks kind of long, what we're talking about is like an accelerator pedal. As we push it down, there's a little pivot point at B. So basically what we have is, we have a straight shot going from point C through point B to point A. And at A, we are pushing down with a force of 16 newtons. And we're told that the distance along the foot pedal from A to B is 170 millimeters. And the distance along the foot pedal from B to C is 80 millimeters. And it says it's hinged at B, knowing that angle alpha is 28 degrees. And we're told that that is 20 degrees. Okay. Knowing that find the moment of that 16 Newton force about point B by resolving it into horizontal and vertical components. All right, so here's the deal. We have to use a little bit of trig here, but basically the force and the distance, which is called moment arm, both have X and Y components. So we're going to write both of them as vectors using the X and Y direction. So let's take a look at the pneumatic foot valve first. The pivot is here at B. That means that the moment is going to be about point B. It's going to start here at point B and extend up to point A from my moment arm. And so that vector looks like this. All right. The distance from B to C does not really affect this equation. I mean, it's a place where, in terms of design, the valve will, the foot valve will rest at point C, but in terms of creating a moment, the moment's created about point B because that's the pivot point. Okay, so B to A looks like this. So what does that mean? Well, if this angle is 20 degrees, that just means that these angles are all 20 degrees. So if we look at this, this is what we have. So how do we write the vector BA? Well, first of all, in the x direction, it goes from right to left, so it's a negative. What is this distance? 170 millimeters. Strongly recommend that you turn things into base units right away. So instead of writing 170 millimeters, I would write 0.17 meters. So it's going to be 0.17 meters times the cosine of 20 degrees in the I direction. Now in the J direction or in the Y direction, it's positive because it goes up from B to A. So it's going to be plus 0.17 meters times the sine of 20 degrees J. All right, and you can work that out. Now, the next thing is, if we want to get this angle, this 28 degrees, it's not taken from the horizontal, is it? It's taken from the foot pedal. So how far is the force applied? What angle is the force applied from the horizontal? Well, if you use alternating interior angles, you can see that this is going to be 20 degrees, right? So if you creep it up here, what does that mean for this angle? This is parallel, parallel. So this is 20 degrees. This is 20 degrees. If this is 28 degrees, that must be 8 degrees off of horizontal, right? All right. So when I draw my vector, my force vector, it looks like this with an 8-degree angle. And to write the force in vector notation, I can see that in the x direction, it's negative because it goes from right to left. So it's a negative 16 newtons times the cosine of 8 degrees. And in the y direction, it goes down. So it's also negative. So then to find this vector, what we're going to have is the moment about point B is the moment arm, which we call R, crossed with the force, which in this case is going to be that vector B to A, crossed with the force. So I'm going to leave you guys here to do the rest, but what you'll do is you'll get numeric values for this, numeric values for this. Then you'll put that into that determinant, IJK, with the first components being B sub A in the x direction, B sub A in the y direction, B sub A in the z direction, and then F in the x direction, F in the y direction, and F in the z direction. And then solve, as we did with our other two vectors.
So, the direction is 0?
Yes, that is correct. So in other words, you're going to put 2 zeros here. And what you'll see is that the math is going to simplify really quick because 0 times anything is 0. Yep, good question. Well, if you always start with a 3 by 3 determinant, you will be much less likely to drop a sign or less likely to do arithmetic mistake. All right. Right. It's, if you look at this vector right here, it's a great question. If you think about x being positive this way and y being positive this way, it's negative because it goes to the left in the x direction, but it's positive because it goes up in y direction. All right, well, there's a bunch of stuff for you guys. So I'm going to go ahead and stop recording, but we will have class Monday. I don't have any events that I'm going to lose time on campus for the foreseeable future. But as always, even if I am off campus, I'll be available through Zoom or text. But I should be here pretty much for the foreseeable future. So stop by my office or set an appointment if you have any problems. And otherwise, I will be here Monday and we'll talk some more about moments and vectors. All right, sounds good.